Hey guys, I'm going to get right to it here. We're going to start going through some atoms, molecules, and water notes, kind of some really introductory stuff. Let me get up the full slideshow so hopefully you guys can see this a little better, a little bigger. Okay, there we go. Also want to try and see if this pen is going to work this time. It was not working earlier. Let's see if I can pick a color to draw here. Well, no. It lets me pick the color, but it's not letting me draw. Um, let's see if I can, like, not sure what's going on, but I'll just have to do my best with the pointer and kind of go through things. But anyway, big ideas. How does the structure of atoms allow for interactions with other atoms? What types of interactions take place? And how does the structure of water give it so many important and diverse properties? So those are the big ideas that we'll be going through. I will tell you with this set of notes, even in the in-person classes, I kind of breeze through the beginning of it. Like it's super basic kind of periodic table chemistry. By the way, you should have had chemistry by now, either chemistry, pre-AP chemistry, or AP chemistry. You have to have some level of chemistry as a prerequisite for this class. So if you haven't, you might want to talk to your counselor or email me and we can work through it. It's not that you can't stay in the class, like I'll work with you, but it could be a bit challenging through the first unit and a little bit more at different times during the year. If you've never seen chemistry, you might be a little overwhelmed as I move quickly through some basic chemistry stuff. So here we go. So as you guys all know, everything you see is made of atoms, and so they're super small. They can be clumped together. They can form solid, liquid, or gas, depending on how they're arranged. And then, you know, atoms make up the matter, and a lot of that matter is living, which is why we talk about the chemistry in biology. A lot of chemistry is what dictates what a lot of happens in biology. So that's why we kind of do this biochemistry unit. So just some like more quick reminders here: protons, neutrons, and electrons. Your protons and neutrons are in the nucleus. Your neutrons are neutral. Your protons positive. Your electrons are negative, zipping around the outside. Okay. Isotopes, we do talk about isotopes a little bit. You should remember from chemistry as well. So in this case, we have carbon 12, carbon 13, carbon 14. So if you stop and think about where carbon is on the periodic table real quick, it's number 6. So it has 6 protons and it has 6 electrons. And in the original carbon 12 over here, it has 6 neutrons. Okay. But isotopes vary in their number of neutrons. Neutrons do not change the charge, they just change the mass. So that 12, 13, and 14 have to do with the mass, the average mass of those isotopes found in the world. And so that's why they change a little bit, and it makes them behave a little bit differently sometimes. Okay. So if we look at our next isotope slide here, and I'll hopefully move my head out of the way. It is really delayed here. So isotopes have unstable nuclei. That's what makes them radioactive. They spontaneously emit particles, and we have machines. We have technology that can pick up on that, and we can see where there are things that are radioactive. So we use this in biology. We use this in medicine all the time. Maybe you have had to drink some dye. You've been to the doctor maybe, and you've had to have something diagnosed. This happens a lot, like in our digestive tracts and things like that, where they want to see exactly what's going on. Or maybe your parents have, you go to the doctor and you might drink a little cocktail that has some sort of radioactive isotope in it. And depending on what isotope it is, it gathers in a particular place. So if you look over here at the picture over here, you can see the little glowing part right there, the cancerous throat tissue. If you're not sure what that is, think about what type of cancer typically occurs right here, and that is where your thyroid is. So you will see that sodium collects in your thyroid. That's where a lot of the salt intake that you bring in collects. And so they can give you a radioactive cocktail to see that, and they can take pictures over time and see if your thyroid is enlarging or getting smaller depending on the treatment and progression of cancer. So that's one way how we use isotopes in biology. It is radiation can also be quite damaging. Radiation tends to like rip through cells. You've probably seen that if you have anyone that you know of has radiation done, they shoot kind of lasers through there, and it kind of rips up your cells and tears them apart. So you have to be careful how many radioactive things you give a person. You do have to be careful about that, but sometimes there is some damage relating to the diagnosis. So major elements in biology. Hopefully you remembered CHON. You have carbon, hydrogen, oxygen, and nitrogen. A lot of times sulfur is included in there as well. Some of the molecules we'll talk about have CHONs, have all of them in there, or even phosphorus, CHOMP. So carbon, hydrogen, oxygen, nitrogen are in a lot of the things. And I have to slide my head up over here again. Probably going to keep happening with each of the slides. You have about 10 minor elements beyond that, and about 50 trace elements that are in really tiny amounts. But this chart kind of gives you some idea of that. So you need to manage your nutrients, or else you can have some disorders. If you don't have the proper amount of nutrients in your diet, you're going to get some disorders. You can see our man down here in the corner definitely has a problem right here on his throat. It's really enlarged. Okay, and that's called a goiter, G-O-I-T-E-R. That's called a goiter, and that can happen with your thyroid if you have a salt deficiency. That's what can happen. So people that live in parts of the world that don't get a lot of salt can have run into these problems with goiters. And then the picture there in the middle also talks about plants. Plants need the same thing, right? If you've ever watched your parents put fertilizer on their yard, you're giving the yard nutrients. You're giving it, for the most part, nitrogen, phosphorus, and potassium, which are the three big things that plants need. And you'll see, based on the leaf color there, what happens when they don't have that particular element versus a healthy leaf. So that's really what we're putting on our yards when we go to the Home Depot and buy some fertilizer. There'll be 3 numbers on that bag, one for nitrogen, one for phosphorus, one for potassium. And you can buy fertilizer in different amounts based on what your yard actually needs, or what your plants need, or whatever the case may be. Energy and atoms. So energy interacts with atoms in different ways. So really what's going on here is we're just looking at how electrons are moving within the elements. And so they can move to a higher level and they can move to a lower level. They just can't be caught in between. They have to be on one level or the other. Okay, it's kind of like a bookshelf. You can either put the book on the first shelf or the second shelf. You can't put it in between. Okay, so it has to be in one place or the other. And so if you look like the ball bouncing down a flight of stairs, that's usually an analogy that gets used for energy of electrons. So they can kind of, be on one step or the other, and they can move between the levels, but not really in between. Okay. So, and, energy being lost or absorbed kind of moves those electrons between the shells. You can see the diagram right there. Couple bonds we'll talk about, the typical ones that you guys are used to. Ionic bonds, where electrons are being traded. Okay, so this is a simple ionic bond where electrons are being traded between elements. You've probably seen the salt example quite a bit. You have sodium and you have chlorine, and so one of them, sodium, has an extra electron in its valence shell, and chlorine really wants one, so that makes a good match, right? The two of them, one of them gives up an electron, the other one takes one, and then that attraction is what holds them together. And so when you look at them individually down here in the pictures, sodium's a metal and chlorine is a yellow gas, and when you put them together, you get this white powder that you put on your French fries. So it's kind of weird. There's a term for this, and it's going to come up later in this slideshow, so I won't say it just yet. We'll use it as an example later. Covalent is the other one. Covalent is when they share electrons, right? Tons of combinations when you're talking about sharing electrons, and this really has a lot to do with why carbon is found in most or all organic molecules. It's super important biologically. So oxygen shares electrons with hydrogen to form water. And then, like I said, carbon shares a lot of electrons with other things covalently, and it forms all different sorts of shapes and sizes and structures, which then dictates different functions. Okay. Polarity has a lot to do with where these electrons are. If the electrons are not being shared equally, then there is an unequal distribution of charge, right? Electrons are charged negatively. So if they're not arranged around the molecule equally, then there's going to be a charge. There's either going to be a positive or a negative charge and how things attract to each other. So let's just look at water as an example, right? So typically, if you think about the periodic table, hydrogen is 1, so the 1p in those circles is for 1 proton, and then oxygen's number 8, so 8 protons in that circle, okay? So also those number of electrons, right? Hydrogen has 1 each, oxygen has 8, okay? But when you think about how valence shells work, you have 2 on the first and 8 on the second. So oxygen's not really happy by itself, hydrogen's not really happy by itself, but when they share these outer electrons together, then hydrogen would have 2, which it needs, and oxygen would have 8, which it needs. But now focus on where these electrons are and where they're going to spend the most time, okay? So if I kind of fast forward this, I got my big, strong polar bear looking cartoon guy here because he's controlling, he's much bigger, right? He's a much bigger atom and he has a lot more of the electrons than the hydrogen. And so these pink circles are going around to how electrons move and they go around the nucleus. Well, the vast majority of them belong to oxygen. So they zip around that oxygen way more, and then every now and then they'll go around to hydrogen. And then they go back to oxygen, and then they'll go around to hydrogen, and they go way more around the oxygen. So if the oxygen is where all these electrons are hanging out, are we sharing the charges equally? Not really. So where is the negative end of this molecule? Well, it has to be on the oxygen side, where the more positive side, meaning where the electrons are not, okay? Because if you take away the negative, it becomes positive, okay? So the hydrogens are way more positive end of the molecule, and the oxygen is going to be the negative end of the molecule. And since we have an unequal distribution of charge, a negative end and a positive end, we have a polar molecule. Water is a polar molecule because of this, okay? Hydrogen bonds are also another type of bond we'll deal with. By themselves, they are kind of a weak bond. But if you put a bunch of hydrogen bonds together, they can be pretty strong, okay? So very good qualities to have actually in biology, especially for DNA, okay? You can also look at the water molecule here. So water molecules themselves, the oxygen and the hydrogen, okay, we just saw they have a covalent bond. But the bonds between the molecules, the dotted lines right here, I wish my pen worked, but it doesn't. The dotted lines right here in between each of the molecules, those are hydrogen bonds. Okay, so covalent bonds within each water, and then they're hydrogen bonded to each other. And as you can see, it's a hydrogen and an oxygen in between each one, each of those bonds. Okay, if you think about DNA, how are these qualities advantageous to use hydrogen bonds between the bases? Well, DNA is this double helix, right? Hopefully from regular bio, you remember that sometimes we have to unwind that helix and we have to separate them in order to copy this side and this side in order to replicate, replication, in order to replicate the DNA, we have to make copies. So we unzip the double helix and we get rid of the hydrogen bonds, but they can very easily be formed again. So we unzip them, we do our copying, and then they form right back together again. So it's a really advantageous system for that. Okay, so polar molecules, you can actually tell by how they look. Okay, if you just look at a molecule on a piece of paper, just a 2D image of it, look to see if any part of the molecule is winning the tug of war. So in this first molecule, you'll notice that there's a C in the middle and there's 4 H's, so they should be pulling on each other equally in all directions. Okay, so that should be a hint. And then on the bottom one down here, you look, and now we've added an oxygen in. So which one of these molecules looks like the tug of war would be equal, meaning they'd be pulling in, as much in one direction as the other, and which one looks like it might be pulling stronger in one direction? Hopefully you have figured out by now it's the bottom one, okay? So if you look at the charges that go around this thing, the top molecule is not polar. They're sharing the charges equally around that one. The bottom one is not sharing equally because of that oxygen. It'll be pulling more negatives that way. So that molecule is indeed polar. Okay? So we talk about polar molecules a lot when we talk about the words hydrophilic and hydrophobic. So these are molecules, hydrophilic molecules that will form hydrogen bonds in water. So these are water loving. Okay, so hydrophilic is water loving, and that means they're going to be polar because water is polar, and polar is going to dissolve polar. Okay, polar cannot dissolve nonpolar. So any molecules that dissolve in water are going to be considered hydrophilic or polar. And so it kind of looks like this. Because they're polar, there's all these plus and minus charges on all these different molecules, right? Water has them, and this molecule has them. So now all these, let me go back one, all these molecules have the charges attracting to one another, and they're all mixing in kind of together, and that's going to allow it to dissolve in water. If we look over here, a hydrophobic molecule, get me out of the way, a hydrophobic water molecule, hydrophobic, water-fearing, okay? So these molecules do not like water. They are water-fearing molecules, and they're not going to dissolve in water. So if you look at the one that pulls equally, there's no charges there. There's no external positive or negative charges because they are pulling equally. So the water doesn't want to bind with them, okay? It doesn't want to bond with them at all. All the waters can go together, okay? But if you look down here inside the circle, these are all the carbon-hydrogen molecules, the methane molecules, and you can picture like a bubble forming inside all of that water molecule around it. So picture like dropping a drop of vegetable oil into a cup of water. You can always still see that drop of vegetable oil when you do that. That yellow vegetable oil doesn't dissolve and it all becomes clear. You can just see that bubble hanging there in the water, okay, because that vegetable oil is non-polar and the water can't dissolve it. Okay, so that's how you can kind of think about this. So bonds determine shape. Okay, how all of the things, how all of the chemistry bond all of these different molecules, that's going to determine shape, and shape is enormous in biology. Okay, so shape dictates structure, and structure dictates function. They are always related. Okay, structure and function are always related. You are going to hear this a lot this year. Okay, and so couple quick examples. If you look over here to the left, you'll see the natural endorphin. And an endorphin is what happens when you're kind of exercising or you're running or you get excited. You'll have some natural endorphins. It's kind of what makes you happy, and you feel a little euphoric if you do, like, this is what they call the runner's high. If you like run a really long time, like a marathon or more, and there's so many endorphins in your body that you almost don't feel that your legs hurt anymore because it's almost like a natural drug that makes you block out the pain. Well, morphine is a very similar shape to these endorphins, right? And morphine's a very addictive drug, but it is a painkiller like that you can get in hospitals and things. And so look at the shape of those things. And for the part down here in this bottom diagram, the part that binds to this cellular receptor, the shapes are identical. So if someone is giving morphine, then that morphine will bind to those endorphin receptors, and it will tell your brain that that you have these endorphins, and it will start messing with the chemistry of your brain, and it'll make you not feel pain very much. Okay, it'll start giving you that little high to get there. So you might know people that are in hospitals that have had surgery and they have a little morphine drip to deal with the pain after surgery. And so that's kind of how that goes. It's because the shape is the same, and shape determines how the structure and function deal with each other. So we'll be looking at a lot of structure and function examples throughout the year. Chemical reactions, when you are forming and breaking these bonds, we're going to be looking at this and how some of the reactions take place, especially when we get to things like respiration and photosynthesis. These chemical reactions are going to come in handy. So compounds and emergence. So this is the term I was going to tell you. This would have been one of your summer assignment questions, and I still may give it to you just as a reminder question. But emergence, the definition here, increasing levels of complexity in a system can cause new properties to be seen that were not present in lower levels of that system. Okay, so here is our salt example again. So we have a shiny metal and we have a yellow gas, but when you put them together, so when we put sodium and chlorine together, that is more complex, right? But that changes the properties of what you'll see, and you get this white powder. So the white powder and all of those properties emerge from the more complex sodium chloride. Sodium by itself doesn't have it, chlorine by itself doesn't have it. When sodium chlorine goes together and becomes sodium chloride, now we have this whole new property that wasn't there before. That's emergence, okay? So we will again talk about emergence and how things come about in a more complex level that were not there in lower levels of a system, okay? That'll keep coming back as well. So why learn about water in biology? Is water living? Is it? No, of course not, okay? Water is not living. However, life occurs in water, okay? All of our cells have a ton of water in them. You guys probably see the picture on the left quite a bit in a textbook where all the organelles are colored in, but look at the one on the right where all the organelles are white and all the space, all the negative space is now blue. That's how much water is in a cell. That's why we say cells are made of so much water. And that's why we say your bodies are made of so much water, right? All those numbers are in like the 70% range or something per cell and per body and actually per planet, right? They're all somewhat proportional. We do have to talk a lot about water and how it plays into life on Earth, okay? So water is pretty abundant, right? We have 70% or so of the planet being water. The problem is not all of that water is usable. Very little of it is usable. If you go down here to this diagram in the corner, about 3% of the water on Earth is fresh water. And when you take just that 3% and you break it down, so here's your freshwater column in the middle now, the brown one, okay? Of the 3% of freshwater, of that 3% on the planet, about 68% is ice caps and glaciers, frozen. And 30% or so is groundwater, and there's about 1% of other stuff, okay? So if we just look at like the 0.3% of surface water, now you're getting into fresh water. Now you're getting into lakes and swamps and rivers and stuff like that. So while we do have a bunch of water on the planet, at some point we may need to figure out how to really convert salt water into something that's more usable. There are plenty of people that have done this and tried to do this. It's just way too expensive right now to make it worthwhile for any company to take on. They'd all go bankrupt. Remember, water has many special properties, all of which is due to its polarity. Polarity is going to dictate all of this. And then as the top says, water can be a solid, liquid, or a gas, all at normal conditions, like no crazy temperature or anything. You can cool it and get it to freeze, and you can warm it and get it to a gas, but those aren't outside of normal. Those are still under normal conditions. But polarity, water's polarity is kind of the big thing that gives it all these properties. So the first one is cohesion. Okay, you might have seen things like this before. Cohesion is the hydrogen bonding between the water molecules. So water seems sticky. It seems like it sticks to itself, right? Water, whenever you have water droplets on a windshield, they stick together and then they run down together. The same in your shower, okay? And then you can see the picture up top here where you have like this water strider on a pond here, and you can see his feet are making imprints in the water, but they're not breaking, and that's because of that cohesion of the water molecules. So cohesion is water molecules sticking together, water molecules sticking to other water molecules. Adhesion, the one below, is water molecules sticking to other things, okay? So hydrogen bonding between water and other substances. So this brings on things like capillary action and a meniscus. I know you went through chemistry, so if you look at the meniscus here, you probably learned how to measure, how to read it based on the curve of the meniscus, because it doesn't sit flat, because the edges are wicking up the side of that cylinder, because the water is sticking to the glass side and it's wicking up, so it doesn't stay flat. That causes that little curve called the meniscus. Okay. Same thing. Trees. How does water get to the very top of trees? Well, the rain doesn't hit the trees up top, and the leaves, absorb it. The leaves don't absorb it. It all comes in through the roots, which is on the ground. Well, what happens when your tree is 200 feet tall? The water has to work its way up the tree against gravity. Okay, so there are little tubes in plants called xylem and phloem, and they are working the water and nutrients up the tree against gravity to make that work. Okay, so a couple examples for you anyway. Cohesion, water sticking to water. Adhesion, water sticking to other things. Water has a very high specific heat, right? So that's how much heat has to be absorbed or released to get the temperature to change. Okay, so sometimes you like think that pot on your stove is going to boil before it does. Well, it takes some time. You have to put in a significant amount of heat, and the more volume of water you have, the more heat you have to put in, right? And so that's why when you look at this diagram down in the corner, think about where are all the warm cities in our country. Well, you have Southern California, you have Florida, you have places down in South Texas, Galveston and Houston, because they're all near large bodies of water and the temperature doesn't fluctuate very much. And so things really change very slowly. Even Seattle's not warm, but if you look at their temperatures, because they're right up against the ocean, they stay in a much more consistent range than, say, us in the middle of landlocked USA, and we have all 4 seasons, and we get frozen and we get boiled. So, we have drastic temperature changes because we don't have that large body of water there to buffer the temperature for us. Okay. This one down in the corner, evaporative cooling. This is really how your body cools itself when you sweat. So, yes, the water does feel cool on your skin, and that can lower your temperature. But the real reason you cool down when you start sweating is the sweat comes from inside, right? It gets out through your pores. Well, those little droplets that come out have heat trapped in them, and the heat is moved from the inside of your body to the outside of your body, and then the air starts wicking the sweat away from you, and the heat gets released into the atmosphere. So it's taking it from your body and moving it out into the atmosphere, which is cooling your body, and that's called evaporative cooling. And by the way, this is why your dog pants when it's hot, because it's trying to get all the heat out of its body and into the atmosphere and cool its body down. A few others. So ice floats, so big deal. We all know that from putting ice in our waters and drinks and stuff. So what does this mean for biology? Well, think about for a second. What if ice didn't float? What would happen to some of the aquatic life if ice didn't float? That would not bode well for anything in a pond or a lake, right? So when things freeze over, that ice would sink, it would crush everything. It would not allow oxygen to be there and stuff like that. So that would be a problem. Water is a tremendous solvent, but it's not a universal solvent. There really is nothing that will dissolve everything. Water can dissolve a ton of things. Like, I'm sure you've just taken water and gotten stains out and gotten food out and all sorts of things, but it doesn't get out everything. So what can't water dissolve? Stop and think about that, or pause the video for a second. What can't water dissolve? Water can't dissolve nonpolar things, right? If any of the molecules are nonpolar, water can't dissolve that. There are a lot of polar things that it can, but it can't do anything nonpolar, okay? And then on this end, just water dissociates. That word dissociates means comes apart, okay? So weak hydrogen bonds allow water to dissociate. And so when you have a water molecule, because there is that weak bond there, depending on what you're putting it in, you can have the hydrogen and the hydroxide, right? The OH minus, that's your hydroxide, they'll separate. So it'll go from water to an H and an OH, okay? And so, oops, sorry about that. So as far as the pH are considered, so that's gonna be neutral, right? Because you have a positive and negative, positive H, negative OH, that's still neutral. So acids have more hydrogens and bases have more hydroxides. I'm sure you remember this from regular chemistry, and then how to hopefully tell them apart as well. When you have an acid, you have the H written in the front, and when you have a base, you have the OH written in the back. This is just like an example scale, things that are acidic and things that are basic in how they go. So, and this just kind of shows you how things are written, right? So if we have hydrochloric acid, the H is in front of the chlorine to show that it's an acid, and then the other one down below, you have sodium hydroxide, which is a base, and the OH is at the back. Okay, so that's just how they're written. Anytime you see an OH at the back, it's probably a base, and anytime you see an H in the front, it's probably an acid. And then you can kind of see how strong these things are right here. Oh, I do want to mention one thing though. If you look at that scale, it just goes from 0 to 14. That word logarithmic, okay? That word logarithmic means by tens, okay? By a scale of 10. So when you have a 3 or a 4, first of all, which one's stronger? Is a 3 stronger or a 4 stronger? Pause the video if you want to try and answer. You do need to try to make yourself answer things before I tell you, okay? So the 3 is stronger than the 4, Okay, because if you look, that means it's going to be more hydrogens. To the end of the scale, the lower part of the scale, there's going to be more free hydrogen. And that's because neutral's in the middle, right? 7 is neutral in the middle. That means there's an equal number of hydrogen and hydroxide, and there's no big change in the middle there as far as charges and stuff. So they cancel each other out, and that's more neutral. The farther you go north on this diagram, the farther you go up, you're getting into more and more acidic things, and the farther you go down, you're getting into more and more basic things. So back to the original question. A 3 is stronger than a 4. Well, how much stronger is it? Because it's logarithmic, a 3 is 10 times stronger than a 4. So how much stronger is a 2 than a 4? How much stronger is a 2 than a 4 if it's logarithmic? Okay, you might be tempted to say 20 because a 3 was 10 times stronger than a 4, and if a 2 is 10 times stronger than a 3, well, that's 20 times. Well, the problem is they compound each other. You have to multiply them, not add them. Okay, so a 2 is 100 times stronger than a 4. Okay, so if you look down below, how much stronger, or let's say, is a 10 or a 13 stronger for bases? A 10 or a 13? 13 would be stronger because it's farther away from neutral, right? It's going to have more hydroxides in it. And so how much stronger is that 13 than the 10? If they're 3 numbers apart? Is it 3 times stronger? Is it 30 times stronger? Or is it 1,000 times stronger? Those are your options. Should be 1,000 times stronger, right? 10 times 10 times 10, give you 1,000 times, okay? So make sure you know how the pH scale works, okay? Couple examples, what we look at in pH in biology. pH kind of dictates a lot about proteins and how a lot of molecules work. And some molecules will work in a particular pH while others won't. And so our coral reefs are dying out a lot because of a change in pH. They're becoming more and more bleached. You can see the ones on the far right. You don't see the color anymore, and that's mainly due to a pH change. A lot of the exhaust from the last 40 years of air travel, of planes going across the ocean, a lot of times that exhaust falls into the ocean, and it's changing the carbon level in the ocean. And so it's affecting how our coral reefs are, among other things, but that's one of the things causing it. And so you can look at these tables over here to the right, and we're kind of looking at some enzyme activity. So you can have to see the pH scale and the relative activity. So this one, it's going to perform pretty well at about an 8. But if you go, too much below 7 or too much above 9, it's not going to do very well. Cholinesterase over here, it doesn't do very well in an acid. Okay, but once you get it up to neutral or beyond, it doesn't really matter what the number is. It's going to work great. Same thing with pepsin. Pepsin's very acidic, but it's not going to do very well. The more acid you take out of that system, pepsin's not going to work very well. By the way, where do you think pepsin works in your body? Hopefully you said stomach, because that's where a lot of your acid is, right? Pepsin's one of the enzymes in your stomach that makes that works really well because your stomach is so acidic. And then this one down here, what can you learn from this, straight horizontal line here? That one doesn't matter, pH. It works well in all pHs. So that one's really not particular. Okay. All right. So we made it through this unit here, or this lecture, and here are some practice questions for you. So don't forget to go back and check these at some point. Hopefully this helped you. Let me know if you have any questions. Thanks.